So previous models gave us the basics of regression. So by this point, we should be familiar with the following concepts. That a regression equation is used to predict a value, called the dependent value, based on a number of independent variables. That the formula for the regression is going to be the form of y hat, which is the predicted value, equals beta 0 plus beta 1 x1 plus beta 2 times x2 plus all the way beta n xn plus some error. Y hat in the formula is the predicted value. The betas in the formula represent the coefficients or the multipliers of the independent variables. And epsilon is the equation that represents, epsilon in the equation represents error in the model, since no model is ever perfect. The standard error of the estimate is a metric that represents the approximate error of the general prediction. And the adjusted R squared is a statistic that represents the amount of variance in Y explained by the regression model, and is used as a means to determine how well the model is performing. Now, in all of our previous models, our independent variables have been continuous variables, not categorical. Remember, the categorical variables are variables that are qualitative in nature, such as gender, male, female, risk level, low, medium, high. If we wish to include the effect in our regression model of qualitative variables, we have to use what's known as a dummy code. We're basically converting it from some qualitative mnemonic to a 1 or a 0. Now, many statistical applications and some add-ins for Excel handle this easily, but we really should know what's happening. So dummy code represents a qualitative value with a 0 or 1, male or female. Because gender has 2 levels, male and female, this is easy to understand. But what happens when we have a variable with 3 levels or more? So on the right, we have a table that we've used in a previous model. However, we're now including another variable for the location of the department. The location of the departments can be New York City, Chicago, and Dallas, respectively. Now, in order to dummy code this, one might think, well, I'll just number them 1, 2, and 3. But consider what would happen if you interpret it as such. Remember that the regression formula creates a coefficient in front of the variable. In this case, it would have been department. Since department would be 1, 2, or 3, it's interpreted as a unit increase in department would yield some beta coefficient increase in Y. And so we would be saying that there's a ranking order to New York and Chicago and Dallas, that if you increase from one to the other, that you end up with an increase in Y or a decrease in Y. And that's not really what we want to say. We want to know what the difference is between each one of the 3 cities. So let's see how to handle the dummy variables and include them in our regression formula. What we need to do is create a variable that would be 1 or 0 for New York City, as we've done here in the 5th column. Then another variable in the 6th column would be 1 or 0 for Chicago. Now you might think you'd need another variable that would be 1 or 0 for Dallas, but we don't. If New York City is 0 and Chicago is 0, then the department must be Dallas. And we can see that down below in the last few entries, where 0 and 0 will refer to Dallas. So we just need to add those 2 columns into our data set and into our regression. The department column is left for you to see how it was changed. Now our regression model contains 4 independent variables: complaints, sales, the New York City field, and the Chicago field. When we run the regression using only 4 variables, we identified the 2 continuous and 2 dummy-coded variables, and we get the regression values below. You can see that we have an intercept of negative 19.27, the coefficient for complaints is 0.98, the coefficient for sales is 0.01, and New York City is 1.59, and for Chicago it's negative 0.50. So let's see how we interpret these values a little bit more closely. First, we can see that we have an adjusted R squared of 0.839, which means that 83.9% of the variance in Y is explained by the model. Next, we look at the coefficients themselves. The x1 and x2 variables are interpreted as we had done before. So we have our 0.98 and we have our 0.01 for complaints and sales, respectively. And interpreting the location of the department is actually pretty simple. Since the coefficient is 1.599 for New York City, we would say if the observation is in New York City, add 1.599 to the number of complaints. If an observation is from Chicago, we would subtract 0.502 from the complaints. Well, what about Dallas? Well, if it's not New York City, we won't add the 1.599, and if it's not Chicago, we won't subtract the negative 502. Dallas is exactly the fact that we do not add or subtract anything to the coefficients. It's what we call the control. And it's really just that simple. Now, we've highlighted some of the other columns here, so in the final result. So we want to be careful because we're going to discuss those in another module. The New York City and Chicago p-values were highlighted, and we're going to address this later, but right now we're just focusing on the interpretation of the coefficients. So our final interpretation of the model, regardless of the p-values that were there, is negative 19. The number of refund requests equals negative 19.27 plus 0.985 complaints plus 0.020 sales plus 1.6 added if you're in New York City minus 502 if you're in Chicago. And again, if it was Dallas, those last two terms would just drop off because they would both be zeros. 1.6 times 0 and Chicago would be 0 as well. So here's some notes on dummy variables. The statistical applications are going to handle this automatically for you. So we won't have to create ones and zeros. And we might not have to create our individual fields. But it's a good idea to know how this is done, and you might want to do it. The number of dummy variables needed is always one less than the number of levels in a categorical variable. So if our categorical variable is gender, male, female, the number of dummy variables we need is 1 because there are 2 levels. Assume if we had a variable called risk, the levels are high, medium, and low, the number of dummy variables we need is 2 because the levels are 3. And if we had an age bracket of 18 to 30, 31 to 40, 41 to 50, 50 to 60, and 60 plus, we have 5 levels, so therefore we would need 4 dummy variables. The dummy-coded variable that is missing is always considered the reference category or control, and it does not matter which one we use as the reference.